Again, any last minute questions before the old stuff that we're going to be testing on, or any clarifications? If not, we'll just continue on with SN1. All right. Okay. So SN1. So we're still talking about substitution reactions, and then we're getting to more details about how complex this really is. Okay, so last time we talked about the SN1, we studied the kinetics, and we determined that certain reactions, they don't proceed, the substitution doesn't proceed the same way. And we showed that using kinetics. So let's talk about the mechanism of the unimolecular substitution. This is called SN1 reaction. So this reaction is very similar to SN2. Okay. Now I don't know why. This one can't lower down, so I don't know what's going on there. All right. Sorry if you guys, hopefully you can see that. All right. So this works on the substrates that we looked at previously that did not work for SN2 very well because of how sterically bulky it is. All right, so the most difficult step of this mechanism is the very first one. It's forming the intermediate, which is a carbocation. Okay. So this equilibrium here is very slow. It's almost, well, let's go back there. It's almost very little is to the carbocation. All right, so this is very slow. All right, so this is our rate determining step. So this is what controls the rate of the reaction. All right, so we get bromide ion. So sometimes you might ask, like, what's the difference? Well, there is a difference, okay, between these two mechanisms. It has to do with your product distribution and how reactive the starting material, how reactive it is, okay? So here we generate, so carbocations, they're like radicals. They are all planar. So they're sp2 hybridized. All right, and just like radicals, they're stabilized by neighboring carbon groups, all right? So they depend on hyperconjugation. So remember that term we saw before in radicals. The same thing applies for carbocations. But in this case, it's more reactive because it doesn't even have an electron in there. It's deficient by 2 electrons. So this is our carbocation. So this is our intermediate. Carbo. So instead of carbon cation, we just give it a name that just rolls off the tongue a little better. Carbocation. Okay? All right. So this is the first step. First step. Okay, that's the first step. Now, the next two steps, they're considered fast steps, okay? So number 2 is the nucleophilic attack of your carbocation. And this carbon, this is so reactive that any nucleophile nearby will pick it up. So it doesn't matter if it's strong or weak, it will pick it up. It doesn't matter. All right, so whatever nucleophile is around will pick it up. Now, the problem becomes when you have 2 competing nucleophiles in solution. If you have that situation, the better nucleophile will win. All right, and if it's more concentrated, like the concentration is higher, it will also win. But we'll talk more about that later. So let's use this example. So this reaction is fast. So I put the top arrow here, made it much larger than the bottom one. All right, so this will attack. So it can actually attack on either face of this carbocation. So we will have some stereochemical outcomes based on this, but since that's not a chiral center, we don't have to worry about that here. Okay, so this is fast. And next we draw the product here. Okay. OCH3. All right, so this is called an alkyl oxonium ion. All right, so these ions are very acidic. Okay, so this is a strong acid. All right, so it's very similar to, remember, hydronium, similar to H3O+. All right, and remember, the pKa of oxonium here is negative 1.7. So this pKa is negative 1.7. All right, so since it's very similar to hydronium here, the pKa of this particular ion, so the pKa of this guy is very similar. So we're just going to say it's approximately negative 1.7. All right, because it's very similar to hydronium. So that's a very strong acid. Okay, so what do you think is going to happen to the H on that oxygen? Yeah, it'll basically plop right off just in solution. So anything that's just a little basic, we'll pick it off, okay? And that's the very last step. So you can't isolate that. That's a charged species. So that ion, that H, if it's an H atom, it'll fall off really quickly. So the third step is the loss of a hydrogen ion. So we get H3C. Oh, sorry, I forgot the lone pair here. Let's write a lone pair on the oxygen. There's still one lone pair on the oxygen. All right, so now the positive charge here will go away. And we're going to take away the hydrogen atom, or from the ion here, with another molecule of methanol. Okay, so that methanol molecule is going to take away that hydrogen ion. So this step is also fast. And then what we get out here is the product that we want, and that's going to be terbutanol. Sorry, not terbutanol. This is an ether. All right, and what we get out here is this one, CH3 OH2. So this extra proton here, or the H+, is just going to be floating around solution. So it's going to kind of be shuttling between, or traveling between different methanol molecules, CH3OH. Okay? So the biggest hurdle here is finding the carbocation and making that one, right? So that's the slowest step, because that intermediate is not very stable. And that's why this reaction, it only occurs for the most substituted substrate, right? The most tertiary substrate, because if we had a primary carbocation, that's not really very stable. It's not stable at all, so it rarely forms. So that's why it never occurs during our SN2 reactions. We never saw carbocation form at all. Okay, are any questions on the details of the mechanism? All right, so for mechanisms like these, you will be expected. You don't have to show the equilibrium arrows, but you should show arrows that show the production of all your atoms that come off or form a bond, and you have to show formal charges. Okay? Yes, Catherine.
Would this also be kind of like the mechanisms for the like monocoordination, monocoordination, where like then repeats because of the
Yeah. Oh, you could kind of think of it like that. Sometimes it can go backwards, but yeah, this methanol molecule, that hydrogen would probably, so that H plus will probably just pair up with the Br minus that's in solution up there. And then, yes, methanol will then go right back ahead and redo the entire process over again. Yeah. So it's all connected there. So the mechanism really just shows you the events of one instance, but this is probably happening to a bunch of these tert-butyl bromide molecules. It's probably happening, several events at once. But we just show one instance of how it's going from reactant to product. Yes. Okay. All right. So we talked about hyperconjugation before, so it's very similar here. Okay. So what determines the stability of the carbocation? So how do you know if the relative rate here? Well, the rate determining step, if we think about the rate determining step, so the rate determining all right, is the formation of the carbocation okay, so remember the relative stability of carbocations, they are the same as radicals. So it's due to hyperconjugation. All right. So tertiary is greater than secondary, greater than primary, and greater than methyl. Methyl does rarely ever forms. All right. So these are not very stable. In order to generate these, you have to have a very extreme conditions. I have never seen a situation where this methyl cation would form like spontaneously. Every time we see methyl, like we add a methyl group because it's partially positive. It's never a full-on cation. All right, so let's just go over an example of hyperconjugation. So let's say we have that radical right there. So this carbon. Now this is where the positive charge is, okay? And then we have a CH3 group here. So I'm just going to write the CH2. And then I'm going to show one of these orbitals here. Okay. Like this. So there's right here we can say here is electron donation. Okay, and then you have another of these orbitals. like this, and they're interacting with the p orbital with the carbocation, okay? And that stabilizes it, okay? So if you have a filled bond and it can interact with an empty bond, it can donate electron density through space. So it's not forming a bond though. So it's just interacting with it. It's orbital overlap, okay? And then this one, we could draw another one here. Now I'm just going to draw the plane here. So we have CH2, hydrogen atom. So this is the orbital interacting with this guy right here. All right. So I just draw 3 lines just so it's clear that that's an interaction. It's not a triple bond. Those are not bonds. Okay. So right here. So these are orbital interactions. Not chemical bonds. So a carbocation is high in energy. So if we put electron density in there, it'll stabilize it. That's what a bond usually does, right? But we're not actually forming a bond because these are just interactions. A bond can't form this way, okay? That just shows us how stable the molecule is based on its neighboring groups. All right, so this is this guy right here. The tert, oops, let's go back. Tert butyl carbocation. Now we know why some resonance structures we can draw, the positive charge prefers to be on the tertiary position, and that's because of hyperconjugation. Okay. So I did show a video on this with radicals about hyperconjugation. It's a very similar process for carbocations. Okay. All right. Are there any questions about that? These carbocations here. No. All right. So let's move on to the next thing here. Okay. So now let's kind of map out these reaction steps here on the diagram. Okay. So let's draw a line here. All right, so let's do SN1, the energy diagram. All right, well, I hope that shows. Okay, don't want to go too far down or it might not show up on the screen. All right, so remember this is reaction coordinate or reaction progress. All right, and this is energy. All right, so let's say we have this situation here. Boom, boom. Like that. Okay. So here are my reactants. So what's important here is just what do we have as the reactants and the products. All right. All right, and then we have methanol. That's our solvent. The solvent is what causes this to be SN1. Because if we tried to do this reaction like on a primary substrate with just methanol, we get no reaction because it's way too weak, the nucleophile. All right, but first here, let's talk about the first transition state. So this is the first transition state. So TS stands for transition state. So let me just write that out. Okay. So what's happening in the transition state is you have your alkyl halide. And now the bond is breaking to form the carbocation here. All right, so partially positive, partially negative, like that. So that's your transition state. So that bond's breaking, right? And then the intermediate, you have the carbocation. So here are my intermediates. Intermediate. So you notice the second step we drew. So we go back to the second step a little bit. Remember, see, it's reversible. It's fast. So the reason is it's reversible. Even the first step is reversible. See that? Bromine could actually go backwards. Bromine could just attack the carbocation and just reform the reactant. But the key here is that your methanol is your solvent. So there's a lot more of that in the reaction mixture. So you have a higher chance of that event occurring. So that's why it moves forward. Okay? And the other reason is if we look at the product right here. All right, so let's look at the product. So the product here, OCH3. All right, here's a little test. Is that a good leaving group or a bad leaving group? OCH3. Let's see. Well, methanol has a pKa of about close to water, so that conjugate base would be similar to like hydroxide. Is hydroxide a weak base? No. So OCH3 would not be a weak base either. Alkoxides are not weak bases. And so they're strong bases. So those are, in fact, horrible leaving groups. All right? So we have to think about the pKa, but also just think about the strongest acids, the conjugate bases. Where do they appear on the periodic table? Right? They're usually ones like here. Chlorine, bromine, iodine. Those are the common leaving groups I told you about so far that work in SN2. Okay? Or work the best. So that's why it doesn't go backwards, because that's a horrible leaving group once it forms. All right? So let's go back. So our intermediate is CH3, 3, C+. And we also have Br-. So that's our intermediate on our energy scale here. All right, so notice here the carbocation is not as high of energy as the transition state, but still high as an intermediate because it's charged. All right, and it doesn't have an octet. All right, now we reach the second transition state. So this might be my second TS. All right, so here on this peak here, the carbocation is going to be forming a bond with OHCH3. All right, so this is still partially positive. This is now going to get partially positive. Okay, and now this is our second transition state. Okay, so in our transition states here, we actually have a positive charge going on, so that's why we put the positive charge here. Okay, and then it goes down to the second intermediate, which is right here. So let's write that right here. CH3, 3. COHCH3. That's a positive charge. All right. And then lastly, we go to the third transition state. Okay. And in the third transition state, what's happening here is we're removing what from the molecule? Yeah, hydrogen. Good. Thank you. All right. So CH3 here. So we don't break out the CH3 because hydrogen is easier to break. So that's why it prefers that one. H forming a bond now to In this case, let's use methanol. All right, so this oxygen is going to get a partially positive charge. This oxygen is going to lose its going to a partially positive charge. And it's still a cation, so we're going to say it's still charged here. All right, so this is the third transition state. Okay, and then we get to the end. Our products are right here. So here's our products. Okay, and the main product is CH3, CO, CH3. All right, and the other products we get, so we can either have over here in the products as well, CH3, OH2 plus, and Br minus, or you could just write HBr. All right, because either the solvent will attack the H, because the solvent is a better base than bromide because it's a conjugate base of a strong acid, or you could just write simply HBr as well. You can use Br in the third step if you want, but it doesn't really, in our case, it doesn't really matter. Okay, so that's the energy diagram. So a little more complicated than SN2, but if we just realize that, oh, okay, a carbocation is forming, we have one more additional step, okay? So that's why we say the SN1 reaction, it's stepwise. So it doesn't happen in one step, there's multiple steps. Okay, any questions about the diagram? Yeah, Captain.
For the third transition state, that partially positive charge is on
the
original oxygen or the carbon?
No, it's on the oxygen. Let me just touch that up a bit. Yeah, so on the oxygen. There you go. Yeah. No, it's no longer on the carbon, so it's on the oxygen. Thank you. Okay. All right. Okay, so remember when we talked about SN2, there was stereochemistry involved. It inverts the stereochemistry, right? SN1, you kind of flip it, but then you kind of don't. So we're going to talk about that, okay? So let's go, let me scroll down here, okay? So now we're going to talk about the stereochemistry. So there's some consequences of SN1. So it's possible to gain stereochemistry and it's possible to lose it. By gain, I mean you get the other enantiomer, and losing, you lose some of the other enantiomer in the process. Okay? All right. So let's think about this situation. So you have Br. Okay, now we have this guy, CH, C. Let's see, okay. All right, so we have four different substituents, right? And now we're going to do SN2. Sorry, not SN2, SN1, tertiary position, tertiary alkyl halide, and a weak nucleophile. That is SN1, okay? So you get two products here. So let's just draw them. Boom, boom, boom. OCH3. And you get the other one. Now we're getting All right. So the second one I drew, I just switched the OCH3 groups and the isopropyl groups there. So that's where we get the other enantiomer. All right. So this one is S. S, 3-methyl. No, it's not 3. 3, let's see. Let's see. 1, 2, 3. Let's see. 1, 2, 3. 3, no, wait. All right. We got 3-methoxy. All right. 1, 2, 3, right? 1, 2, 3, 4, 5. All right, we got 3-methoxy, 2,3-dimethyl, pentane. Okay. And then this one is the R form. R3-methoxy. 2,3-dimethyl pentane. Sorry, it's not on one line. All right. So, what about the starting material, though? Let's see. The starting material is, what is it? RS. So the one on the left, is that R or is that S? Yeah, good. That's R. Okay. So, because it's a carbocation, you actually get 2 positions of possible addition. Okay. So, this position is if we had retention. So, this is retention of the stereochemistry. All right. So, we kept the same configuration. All right. But here, this is where we inverted it. Inversion of configuration. All right. So this is the problem of SN1. If you had a stereocenter, you squashed it. Now you have a racemic mixture, an equal ratio of both enantiomers now. So this is the problem of SN1. So if you had a stereocenter, you had a set stereocenter, you basically reset it, and now it's 50-50. You don't have an excess of either. So that's the problem with this reaction. All right, so let's explain how that happens. Okay, so let's redraw our product here, or reactant. Sorry, not product. All right, so your methyl group here. And then, well, I wrote it out, but you don't have to, guys. So here. Okay. Well, we know Br leaves, right? That's the first step. The leaving group leaves. Then we get Br minus plus our carbocation. Okay, here's the plus charge. All right, so we know that here's one group, then here's the other group, and then here's the methyl group going in the back. Okay. All right. So, well, we have 2 versions of this carbocation, so let's draw 2 versions of it. Boom. Plus, okay. All right. So this one, your solvent, CH3OH, can either attack from the top face or the bottom face. All right. So if we go from the top face here, you're going to get a structure that looks like this. All right. And then the methanol will come and take away this acidic hydrogen like that. And you get the first product, which is, well, you get your methanol that's protonated now, OH2 plus, and your first product, which was the R isomer, which is this guy. OCH3. That one. All right? So that's how it added from the top face. Now, how about if it attacked from the bottom half of the carbocation? All right, so now let's imagine we drew the same carbocation. So here's from the top half approach. So here's top half approach. All right, now what if it attacked from the bottom half? All right, so now as your CH3OH is going to attack from the bottom. So now we're going to do the bottom approach, bottom half approach. All right, so say now CH3OH attacked from the bottom of the p orbital. So it's going towards the bottom half now. So that means it's going to form a bond coming out from the bottom half, and that's going to give you a different stereochemistry. Okay? So now we have boom, 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 boom. Okay. All right, we still have the ethyl group here. Now, you see here the oxygen from the methanol is going to approach from the bottom half. So I drew it like this. So we have a plus charge. And then methanol, another methanol molecule, will come in and remove this hydrogen. And then you will get your second product here. Along with protonated methanol again. All right, so here's the S form. So the S form of the product, here's the R form. All right, so that's so R here refers to R-3-methoxy 2,3-dimethyl pentane, and S here refers to the S version of this product, S-3-methoxy 2,3-dimethyl pentane. So we get two different products there. Okay, so since the p orbital is symmetrical in terms of, the top half of the lobe is the same as the bottom half, there's no preference for which face of the p orbital that the nucleophile bonds to. Okay, drew the carbon atom. So that's the added layer of complexity there. All right, so are there any questions on why we get to see two different products? Okay. So the best thing I would say to get the hang of this is just to practice, okay? Not just looking at it, but going through the motions, writing out the mechanism, and predicting the products here, okay? Well, that's only half of the story, though, okay? There's actually another thing that happens in this reaction that we'll probably talk about next, okay? But let me see. Okay. All right. So let's just talk about a few more things here for SN1, and then we'll take a little break, okay? All right, but are there any questions on this page? On anything around the arrows? Any questions there? No? All right. So now let's talk about SN1 reactivity. Let's go through the same things we did with SN2, now with SN1, okay? So SN1 reactivity. All right, first let's talk about the substrate. So, when we just run over this mechanism, what was the slowest step? Which one? Forming the carbocation, attacking the carbocation, or deprotonating the final product? Yeah, forming the carbocation, because out of those three intermediates or products structures, right, this is the one that doesn't have an octet. The carbon doesn't have an octet. So that's going to be the hardest to do, okay? So, carbocation, intermediate, will control the rate of reaction, okay? So here, most stable C plus, okay, will result in a faster reaction, okay? So the carbocation is the rate limiting step. So the most stable carbocation will form the fastest. Therefore, that reaction will occur most readily, okay? All right. All right, so I want to put a little tidbit here. So secondary, so for example, on this type of carbocation, secondary, and tertiary. Okay, so secondary and tertiary undergo SN1. Okay? They can undergo SN1. All right. So primary slash methyl carbocations. So these ones here. Like for example, CH3, CH2 plus. So this is primary carbocation. And then a methyl carbocation do not go through SN1 reaction, okay? So these intermediates here, they don't usually undergo, they usually don't form, okay? So you don't see these, so don't form at all. Okay, so these substrates, so primary methyl substrates, so I'll give you some examples, okay? CH3, so this is methyl bromide, and something like this bromide, they're going to do SN2. All right, so they undergo SN2. You never see these undergo SN1. All right. Secondary, tertiary. Okay, tertiary will always undergo SN1. Secondary, you're kind of in the middle. You're kind of undecided. You can't decide what you want to be. All right. So here, tertiary substrates. So tertiary substrates always SN1. All right. So these carbocations right here, they can form. So secondary is in the middle. So in the middle here, I'll put this in the middle. Secondary substrates. Either SN2 or SN1, okay? So it's not the best at either, but it's not the worst at either. So it's undecided. So whether or not secondary substrate undergoes SN1 or SN2, you have to consider your nucleophile. That's the most important part. And probably the leaving group, okay? So here, for example, this would be an example of a secondary substrate. All right? But tertiary, they will undergo SN1. Okay? So can you, this one, it's a secondary one, either SN1 or SN2. All right. So now we kind of classified our substrates here. Primary, methyl, SN2. Tertiary is now going to be predominantly SN1. Secondary, can't tell. Okay? All right. Are there any questions about the substrate? We'll go into more details in a little bit about how to predict which mechanism this reaction undergoes. Okay? But now let's talk about the leaving group. All right, now we're going to talk about the leaving group. So let's put this underneath here. All right, leaving group. All right. So leaving group, important for SN1. Just like for SN2, both reaction has to leave. Important for both SN2 and SN1. All right. So let's just recall some of the common leaving groups. All right. So for these reactions, like we saw before, the most common leaving groups are the halogens. So some common leaving groups, okay, are, so remember we have the sulfonates. So those ones we went over on Tuesday, okay, those are still important. It's pretty good leaving groups. Or MSO minus, mesylate, okay. All right. So they're usually greater than iodide, bromide, and chloride. So these are usually the best ones we see, okay? There's more leaving groups that we'll talk about, but we haven't come across them yet, so I won't mention them yet, okay? All right, so let's make a few comments of which ones are the best leaving groups for SN1. All right, so tosylate. So tosylate, remember this was TSO minus. It's the one, it looks like the first one, the sulfonate, but it has a benzene ring in it, okay? And mesylate, that's when it's just a methyl group. So MSO minus. All right, these are the best for SN1. And that's because they can hydrogen bond. All right. So if SN2, we like aprotic solvents. What do you think we like for SN1? Protic, and that's because these leaving groups here can hydrogen bond with the solvent, all right? So they can form hydrogen bond with protic solvents. So the easier you, so we don't have to worry about the nucleophile now. So we don't have to worry about the hydrogen bonding because the nucleophile, it can be weak. So that the nucleophile is less important here. All right. What's important is forming this carbocation. So if you can figure out a way to solvate the leaving group better with polar protic solvents, you break that bond faster. So you lower the transition state. You stabilize it, and the reaction goes faster. Okay. So that's why this one prefers protic solvents right there. All right. So, all right. So we will. All right. So let's take a 10-minute break, okay? And then we'll come back here and talk about the nucleophile's role in SN1. What the?
Yeah,
what's up?
Test corrections.
All right.
So I labeled the score I got, and then
All right, great,
tried-
man.
Then I labeled which ones I got wrong. Then I redid the whole problem and then
Sweet.
redid the one. I did a couple extra like you told me to do, and then
All right, yeah. So, good work.
okay.
Yeah. See how we did. Yeah. No, it's not. There's a form on Canvas for the quiz replacements, so you fill those out. Yeah. No, it's due by the end of the semester. Yeah, it's not due tonight. No. Oh, those? Yeah, those are due tonight. Yeah, you could either fill out the form or just make sure you record the date and what you talked about.
So it's the tutoring and office hours due.
Yeah, so all the ones that have due dates for today, it's like whatever one, the extra credit assignments that have one with them. Like office hours 1, study groups 1.
Yeah, because it looks like there's one for the second part of the class.
Yeah,
So it's like,
but that's not due yet.
Yeah.
Yeah, don't turn that one in yet.
Go for the. Like this one has more already in the second. Because this one's like CH2, and it's the fourth one, it's the fourth lowest.
I hope you don't consider what she's saying. I said that to you. I don't know what he's saying is S.
And it's not considered the fourth one.
Thinking about like that? This? No, because that's where
That's why I can't
hydrogens in the left table, you said it clears my sinuses out, so thanks, but. I think it's great. I don't feel so bad, like, I'm like, I won't do it. What is this one? I thought if the fluid in your hydrogen is the fourth and the wedge, you must swap it.
Yes, so it's 1, 2, 3.
How come this one's two?
Because, so when you look at it, so the first thing you compare is the initial atoms, carbon, carbon, type, fluorine. So fluorine's the first one. Then you have to look at, okay, what are these carbon bonds? This carbon, this is what drives back to like listed.
CHH.
So this one, this carbon is bonded to 3 hydrogens, so HHH. But this carbon is bonded to 2 hydrogens and another carbon, and a carbon is bigger than a hydrogen. So because of that difference, this is 2 and this is 3.
So it's R.
Looks
and
like
then
R, but it's actually
split
S.
this.
Yeah.
Okay, so if it's the same, go to the next one.
Yeah, and then it's like, okay, then it's like, if this was like a CH2, then like, okay, then it's HHC, and then you go, okay, this is HHC, then you go to this first, which is the dualistic CHH and CHH, and you look at the first element, so like you go, okay, what is that first element then bonded to as well? And you bonded to nothing, and you can then go to the second atom like that.
I feel like I saw I watched the transcript thing, and I was doing it, but I don't feel like these, what we're doing is as part of what he was doing on there. So I'm like, wait, what?
Yeah, so you start to show the basic ones.
Yeah,
I did so many of these, now I'm freaking out over them.
I like start by like, okay, first like list out all the initial elements. And then it's like, okay, the similar ones, and we're like, okay, what's the 3 elements that that's bonded to?
Okay, I
There's no
did
way
get
on
on
the
that.
chemical center, and like I list that out. And then it's like, cause they draw an arrow from like the initial element, that one. And then it's like, okay, they both have like CHH, I'm like, okay, what is that carbon bonded to? Because hydrogen's never bonded to anything, so you don't have that. But it was like oxygen, both are oxygen. And then they're both bonded to hydrogen.
Remember how they connected stuff?
Like, is it the black background? It's a nice voice.
Like, when that carbon to a triple bond, like that, it would be like this. To 3 carbons, but then these carbons are also connected to 3. So this would have 2, 1. Yeah.
Okay.
That's what it was.
I'm just gonna guess.
Right? That was for our method.
Yeah.
On the con, you know, if you're signing and then that was like if you were to draw it, it would be like that, right? Because this one was first one. Oh, how you said. Because this one is like an H and 3 carbons. And then on this one. But let's just say we're comparing this one. It would be 2 right?
I'm scared I can just.
There you go.
I feel like you can.
So this one
To be able
is
to
this
do
right
it,
here. And then 3 C's and then H. That's like that. But technically, like that is just to show how visualize.
But it's just,
That's not real.
But that's not correct.
Yeah.
You see
Yeah.
that? Okay.
Yeah.
Yeah.
For this, it's not a name. R to be invented. How do we know that the R is to do?
This is not a
Okay, the.
Yeah.
Slide. you know. I think the. Okay. Okay, I'm going with that.
Oh, yeah, there's only one carbon.
You asked me about this one, and I explained it to you, but I can't remember
You just have to get a spirit of experience for always convenient. Somebody's doing that. There was here that ordered not. Identical charges. Everything. Just one. And also, if you don't have it, it costs for.
But it gives you the name you can draw it.
There's nothing.
That's how it's all this compound.
But I still go with that.
Oh, that makes sense.
My drawing that SN1 is very just
Configuration.
All right. Dude, now it's too cold. All right, guys. So just a little more until exam, I guess. All right. So a good way to illustrate this solvent model. So look, we have this situation. All right. So if you have proic solvents here, it can actually make strong interactions with the oxygen of the leaving group, and that leaving group has an easier time to leave because it's being stabilized by the solvent. So there's a lot of solvent molecules around. So I just drew two orientations here, but you can imagine it can also surround it from the top and the bottom of our molecule, and that even helps it stabilize it more, and this will speed up the reaction. Okay, so that's the leaving group. So the leaving group is most important here. Notice iodide, bromide, chloride, they're not very electronegative, so they don't have the same interaction as do with the sulfonates, tosylate, mesylate, triflate, etc. All right, so we talked about leaving group. What about the nucleophile? Let's talk about the nucleophile now. All right, so for the nucleophile, all right, so remember last time we stated the nucleophile has no effect on the rate. So that means it's not that important for the reaction, for how it proceeds, okay? So I want to mention here, does not have any effect on the rate of SN1 reaction. Okay? However, there's a caveat we must pivot off of, all right? The product distribution. However, the product distribution would be affected by the nucleophilicity of the nucleophile. What I mean by that is the strength. So which one is the strongest? Okay, so for example, let's say we did this experiment. We have tert butyl chloride. So let's have this group here. All right. So how they determined the SN1 reaction is they took the solvent and they just basically changed the concentration of both the nucleophile and the substrate, and they found that by changing the level of solvent you add didn't actually do anything. So the nucleophile didn't affect the rate, but once you did that, you changed the rate of the concentration of your substrate, and that had an effect. So if they held the substrate constant at a constant concentration, but they tried to vary the nucleophile concentration, it didn't work out. It didn't affect the reaction. So that's how they determined the reaction rate there. So let's say we have CH3, methanol, one equivalent. And say we added sodium azide. All right. So which one here is the better nucleophile? Is it the neutral oxygen atom? Or is it the azide, where it has the more basic nitrogen atom, and that one is charged? The azide. So we would expect a larger product, a major product for this one. And that is what we get. So let me just undo that. Okay. All right, so this is tert-butyl azide. All right, this is major, your major product. All right, and you do get some amount of the ether. OCH3. So you get 2-methoxy first. 2-methoxy 2-methyl propane. However, this is a trace amount, so it's very little. And that's because this nucleophile is not as reactive as azide, so there you have some competition. But one thing I want to point out is that both products are formed at the same rate. And that's because the reason that's the case is because they form through the same carbocation intermediate. Okay. Now, the carbocation, if there were two different carbocations, they won't be both as stable, and so they will form at different rates. But since they form at the same rate, and azide is much stronger, it's going to react with it more. Okay. But the formation of both of them, they form at the same rate because they're going through the same intermediate, which is the carbocation. Okay. So nucleophile here doesn't really play a role unless you have an equal amount at the same time here. So one equivalent. So one equivalent, that basically means you have 1 mole of each in the reaction. So you have an equal amount of them forming the products, but the stronger nucleophile wins out. Okay, are there any questions about the nucleophile? So it's not really important here, but if you have competition, which is sometimes you do, okay, then you will have 2 different products, okay? Well, if you wanted just one equivalent of the azide, you would use a different solvent that's not a nucleophile, such as DMS, well, I won't say DMSO, it has to be protic. I'm not sure which one would work. I don't think there's a situation where you have a choice because most protic solvents are also nucleophilic, so there's that issue there. Okay, because most of them have lone pairs on basic atoms. All right, so now the last part is the solvent. All right, so the solvent and these reactions are faster. And which solvent? Which did we talk about? Protic, good. Reactions are faster. And protic solvents. Okay. All right. All right. So the reason that it's faster in protic solvents is that both the carbocation and leaving group can be stabilized by protic solvents. Through H bonding. Okay, so through H bonding here. So what I mean here is just basically they're more polar. So polar species. Okay, so polar species / ions. Okay, so they're better solvated, or they interact better with protic solvents. All right. Whereas in SN2, if we had the nucleophile is important, so that's why we didn't use protic solvents. They'll interact with them too much, and they'll basically seal them away and won't be able to react. All right, so solvent becomes important. So let's show this by showing two examples of reactions here. So let's say we have tert butyl bromide. All right. So let's just use here water, just water. Okay. And then we get our alcohol. So the H disappears and becomes HBr. All right, so here's the relative rate. So the relative rate of reaction. Okay, so this rate is on the order of, what is this? 100,000, 4 times 10 to the 5th. All right, now let's see what happens if we dilute the water a bit by using a larger amount of a different solvent. Okay. So we're not going to use a protic solvent. We're going to use a polar aprotic solvent. All right, so we have 10% water. And then 90%, so this is so propanone is like acetone. Wait, no, that is acetone. What am I talking about? All right, propanone is the same thing as acetone, okay? That's the IUPAC name. The common name is acetone. So this is the same thing as acetone, okay? I'll just put it in parentheses. All right, so we get the same product here, but the rate is slow. So the rate here is about, the relative rate there is that much time slower. So here, protic solvent plays an important role. Okay, so that's why we use protic solvent instead of aprotic. So then in chemistry here, you oftentimes need a polar solvent, and that just helps stabilize the reaction, parts of the reaction, namely the transition phase, the transition state. If you stabilize that state, the reaction can go forward, okay? If that energy is too high, we say that reaction is forbidden, okay? So it's always about the transition state. How do we stabilize those atoms trying to rearrange to form a different product? Okay. Are there any questions about solvent? So if you have an SN1 reaction, you want to choose a protic solvent, all right? Something like acetic acid, formic acid, water, or an alcohol. Okay. All right. Well, I almost forgot. Boop, boop, boop. All right. Any questions on solvents there? No? All right. Hold on. Never forgot. All right. Well, let's see. Forgot to hand this out, so we saw some time. All right. So, all right. Any other questions? No? All right. Let's talk about E1. All right. So, now we're going to talk about our very first reaction. That's not substitution. So remember, we did radical halogenation. We substituted H for chlorine or bromine. Now we're going, and then we did SN2 and SN1, where we substituted a nucleophile for our halogen, or the leaving group. Now we're going to basically remove the leaving group and form an alkene. Okay, so this is called unimolecular elimination. So this has the abbreviation E1. So that's what's called E1, okay? All right, so let's use our example from last time. Let's do the bromide. All right. So what happens here? You add methanol. You're going to lose HBr in the molecule, and what happens here is you get a mixture. So what actually happens in the reaction is you get a mixture of the ether. Okay, so the ether here plus an alkene. So we get an alkene in the mix as well. All right, so what are the product ratios? Well, this is 80%, so as expected, you expect an SN1 reaction. But in every SN1 reaction, you're going to get a little bit of E1 product, the alkene, all right? So whenever you draw an SN1 reaction, you should always write any alkene products. So I'll try to be specific. Maybe I'll say draw the substitution product. Tell me what mechanism forms, and I might have follow-up. You see your product, in your product mixture, you also identify another compound that has a significantly lower yield, okay? Or it may be closer based on the conditions, but usually that's the alkene, okay? So that's SN1, and that's E1. All right. So let's go over to see how this would form, okay? So you get two different products, and that's because the alkyl halide goes through the carbocation intermediate, okay? Sorry, I didn't mean to write it so big. Br. So you're losing Br, right? So you lose Br here, and you get the carbocation. C plus CH3 CH3 CH3. Okay? Well, the methanol molecule here can actually go off into two routes. You can actually use it as a nucleophile. Okay? So we get this product. So this is when methanol acts as a nucleophile. So nucleophile here. Or it can act as a weak base. So when it acts as a base, you may be wondering, wait, aren't those the same thing? They're donating their electrons to form a bond? Yes, but when it's the base, it's not targeting the carbon. It's targeting the hydrogen. Okay? So it's targeting one of these hydrogens here. So here we get the alkene here, okay? So this is the same. So this structure is the same as this one. All right, so we get two different products there. All right, we're going to go over the mechanism next, but are there any questions? So that's called E1, all right? So here's our E1 product. Here's our SN1 product. Okay? All right. So now let's go over the E1 product distribution. Okay? So let's go over the mechanism. All right. So every time you guys see a mechanism, put a star by it. That's something you should practice. Okay? Understanding how reactions work. If you know the mechanism, it's way easier to remember. Okay? But sometimes these things are going to feel like you just have to memorize them. But I want to kind of move away from that. If you practice and understand the fundamentals, I think you can avoid that situation. All right? So let's talk about the mechanism. So the mechanism of the E1 reaction. Okay? So, all right. So what do you guys think happens first? What's going to form? The carbocation. That's our magic intermediate. Okay, well, I won't say magic, but it's the gateway to the rest of our molecules. All right. So, the bromine leaves, and we get Br minus, right? All right, so we're forming a carbocation. Well, let's put the C back. So here's the C. Now I'm going to show one methyl group with all its hydrogens because that's the hydrogen we're going to remove to form the product, okay? All right, so there's a carbocation on this carbon right here. All right, so now let's redraw this carbocation and show the arrows in a separate step, okay? So here we have C, C. All right. All right, let's draw our nucleophile. So our nucleophile is actually a weak base. And as long as you have a reactive intermediate, almost anything that can pick up a proton will actually be a suitable base because your carbocation is so darn reactive, okay? So, doesn't matter which one you take, this hydrogen is going to be removed, okay? I'm just showing this one. You can remove any of them, okay? Because they all line up. All these hydrogens, they all line up with the p orbital like we saw in the beginning of class, okay? So, this now will go over here, okay? So, it's actually forming a bond to the carbon to form an alkene. So now let's draw the alkene. So we get this situation. Like that. All right, so that's the formation of alkene. Yes, Kevin.
You said earlier that the CH3OH was a weak base as a nucleophile. I thought it was a nucleophile are usually strong bases.
Oh, you mean the CH3OH?
Yeah.
Yeah. So they're usually, so it really depends on like which one you are. So if you have a negative charge and you're like oxygen, nitrogen, those are also strong bases. And that's because they're small and the charge is kind of concentrated around the central atom. Yeah.
This neutral.
Yeah, since it's neutral, it's a weak base because there's no negative charge there, only the lone pair of electrons. So it doesn't add that extra strength to it. Yeah. All right. Okay. So we're almost end of time here, okay? So, let's talk about what if you have, so guys, what if you don't have a symmetrical alkene? What if all your alkyl groups are different? Well, that just makes your life a lot harder. All right. So now let's talk about a realistic example of how complicated these products can get. Okay. So I want to reiterate here that you can actually drive this reaction to favor one of the products. All right. If it's low temperature, it's substitution. If it's elevated temperature, you get the alkene. And that has to do with entropy, okay? And the reason why it's entropy is because in an alkene, you usually have more products that are formed. You have the halogen, you have the alkene, and you have the salt. You have the base that took off the hydrogen. In substitution, you pretty much only have the product and the halogen. So you have less products being formed in substitution. So that's considered less disorder. More disorder is when you have more products being formed. So that's why at elevated temperatures, the alkene is favored. Okay? But I just want you to remember, elevated temperatures, alkene. We'll just try to remember that. All right, but let me just talk about the products here. So E1 products of asymmetrical or asymmetric, substituted, all right, so let's use this example. So we have a carbon with a chlorine, a methyl group, and then an isopropyl group. All right. So let's see what happens here. All right. Well, let me just highlight a few hydrogens here. You have this one. So this hydrogen. Okay, boom. You have this one. You have this hydrogen up here. And you have these hydrogens right here. All right, let's try to color code them. So these will be red. So let's circle these as red. These will be blue. All right, and this one we'll just label as black. All right. So if you carry out this reaction in the presence of heat with your methanol, okay, you get 3 different products. So you get this one. CH3. All right. So this one formed when, let's see here. Boom, we got the methyl group. Okay. So this is the, this alkene is from the black hydrogen, okay? So we removed this one. Remove. So you remove the black hydrogen. Imagine the double bond is forming in between those 2 methyl groups. You get this product, okay? But there's 2 more. All right. You can get this one as well. So this is where we remove the ones from the methyl group. So the ones from the blue hydrogens. So remove one of these blue hydrogens. You get this product. Okay? So you see here, this was, if we look right here, this is this methyl group right here that we removed. All right? Because we still have both these isopropyl groups, which is this one. And we still have this ethyl group here, which is this guy. So that's the other alkene product. But now there's one more. What's the other one? Let's see. Well, instead of this one, we have CH3 here. Okay. Boom, boom. Boom. So it looks like we removed this group here. Oh, but this, if we add a hydrogen here, CH2, CH3. So this is from the ethyl group. So this is if we remove the red hydrogen. This one. All right, so we get 3 different alkenes. Okay. All right. So you may be wondering, which one's the major product? Well, there is a major product. It's called Zaitsev's rule. All right, a Russian chemist who observed this back in, I don't even remember, probably somewhere in the 19th century. Okay, so All right, guys. I know it's almost time, but let's just focus a little more. So Zaitsev rule. All right. So what is Zaitsev's rule? All right. In an elimination reaction, all right. So in here, what we get is plus HCl. Okay. In an elimination of HX, okay. So in our case, what is HX? What's X? Chlorine, right. So that'll be our Cl. That's our acid we form, okay? So an elimination of XX from an alkyl halide. All right. The major product is the one that has more substituents. The more substituted alkene product, okay, is the major organic product. All right, there is a reason for this. It's hyperconjugation. Okay, so remember, what kind of orbital does an alkene have that's not hybridized? If you think back to hybridization, right? An alkene carbon is sp2, so what orbital is free? Yeah, so that p orbital, the anti-bonding orbital of that p orbital can interact with the carbon groups, just like we saw with the carbocation. All right, so it's another instance of hyperconjugation. All right, so one thing I want to just sum it up here for E1, all right? So I want to just reiterate, this is the last thing we'll do. So the nature of the leaving group, okay, does not affect the ratio of products of any SN1 and E1 reactions, okay? What the leaving group does affect is how fast the carbocation is formed. That's it. It doesn't affect the ratio on these products, okay? All right, that'll be it. And remember, guys, where are we going? 801, the same room as last time. See you there.